Hello everyone to part 2 benchmark between C++ and Rust language. So in part 1 I did some benchmarking based on simple application. Do some mathematical operation, push it to a queue, and then calculate the time it requires to do this operation for 1 billion element. I got some comments that this is unfair benchmarking because first, standard library in C++ and Rust basically are not the same, so maybe some standard library here or there doing some different thing in how it implements the queue. So this time I will do the exact same benchmarking without using any special libraries or any special data structure. What I will do is basically create a simple structure, and I will do some function members in this structure, do some math. So let's start. Here is our application, very simple one. I started with a struct called simple storage. It has only one member called sum. It's double data type. Now we will have multiple functions. So first one is basically initiating the sum to 0 or whatever the value, so the default will be 0. I will use 0 as a starting for both code in C++ and Rust, and then after initialization I will use this function which is called push all. So this function take one double precision value and then send it to 3 functions inside this struct. So push 1, push 2, push 3. So first function is basically do basic mathematical operation, like taking the value multiplied by this double precision variable and then add it to the sum. Again, push 2 do exactly the same but with different value, and the third push do also the same but with little bit modification. So I used here first multiplication with 2 and then divided by 5, and finally multiply everything in this double value. So when I call push all, it will do all the 3 function here. So first line in main code is basically initiating a new object from this struct. I will give it initial value of 0, and then for 1 billion iteration, again I will use here 1 billion iteration to push the limit to the maximum. So I will simply take this I variable and then convert it to double precision and then send it to push all. So push all will take each value of I and then do all mathematical calculation. After this for loop is completed, I will just print the value. And in order to make it simple, I will just convert it to unsigned integer 64-bit and print only the unsigned integer part. So I'm not interested in the fraction part right now, but we will see some very important note regarding this in few minutes. Okay, the same thing here at Rust. I created the struct simple storage. Again, only one variable called sum is float 64, and Rust is a little bit different in how you would implement function for a specific struct. So I write this implementation block and then write the same exact function. So push 1, push 2, push 3, and finally push all, which do exactly the same. Let's start. Let's open the terminal here. So I have 2 terminal here, one inside the Rust folder and one inside the benchmark folder. So let's first compile the Rust package, cargo, and then build -- release. Yeah, it's completed. Now let's just test it and call cargo run. After the first run, I forgot to mention it was a debug, so it took a lot of time. Here, as you can see, running the debug version of this file. So instead of running debug, I will just tell the compiler build the release file and run this one. Okay, should be much faster. Yeah, here we go, in only like less than 3 seconds. Of course it will have print the same results. So let's clear this out, and now let's run the time measurement bash script, and here we go. Let's do this again. So at each time it just measured 2163 or 62, so it's basically 2 seconds measurement. Let's do this again. That is a good result for 1 billion operation. Let's do this for the C++. Here we go. Let's feed it with the time.sh to measure how much time it would take. cpp.run. Okay, I forgot again the path. So on the first one is 8 seconds, again in second one 8.8 seconds. Yeah, that's a lot because it's -0. Let's do this with -01 to make the compiler optimize it more. Here we go. Let's run the timing benchmark. Yeah, that's way better. So -01 we have now 2 seconds and 169. That is pretty matching the Rust speed. It's even a little bit faster. So we have the same result, the same exact result. So C++ is winning here. So let's do this with optimization flag 2. Yeah, almost the same result. So -02 did not enhance the speed. It's almost the same as -01. Let's do this with all 3. Let's try optimization level 3 but with Clang. Let's convert G++ to Clang here and then run this and measure the time again. Let's see if Clang is faster. Okay, let's run this again. Yeah, it's almost the same as Rust and GCC. It's more matching Rust, so it's a little bit slower than GCC. Like GCC here and -03, 62, 65. No, it's actually matching it. So no difference between running a Clang and GCC for the same code. So what if we use the -0 fast? Like what would happen if we use the -0 fast? Now this is pretty dangerous flag. So do not use it unless you know exactly what you are doing, because it will change the precision of operation, especially if you are using floating or double precision operation. So here let's run the timing measurement again, and voila, we got way faster code. So it's 184 milliseconds. That's a lot faster. That's like a fraction of original speed. But look at this. Look at the output value. It's wrong. It's completely wrong. So C++ and Rust output the same exact value, but here when we use the -0 fast, it's completely different value. If we use the calculator, let's just open the calculator. Let's just delete this here, copy this value, and then let's subtract it from previous value. Now we will have a difference of 21,000. Using a less precision calculation, if you have like very large iteration, it will accumulate error. After all those iterations are completed, the accumulated error, maybe it will be disaster if your application needs high precision outcome. So be careful when you use the -0 fast. So here Rust matches exactly the C++ if we use the -0 1, 2, 3. It matches exactly with all of them, maybe with little bit winning for the C++. Okay, what if the cout here is doing something and make the C++ application slower? Can we remove them? Yes, we can, but we will have a problem. The compiler in the C++ will figure out that test storage had like 1 billion operation, but nothing in the code used this variable. So if we removed this part, it will optimize it out, and actually this value will never be computed. So let's just try this. Let's just comment cout and comment all the include of IO stream, and let's compile it with Clang, do the time calculation measurement, and it's 1. This computation never be able to run in 1 millisecond. It's 1 billion computation. So there must be something wrong, and we know it removed all of this. So actually this is now an empty. To demonstrate this, let's use some reverse engineering magic here. I will uncomment this line, make it back to the original, and then I will compile it with Clang. Okay, and let's rename the output file optimization level 2. Okay, let's generate the same one with optimization level 3, and let's do it also for optimization level 1. So you'll have like 3 executable files, 1, 2, 3. And now let's comment the C out. Let's just comment everything here from the IO stream. So now we don't have any branding for this variable. Now we will say it's an empty or just without C out. I will use an application called Ghidra, which is a reverse engineering framework. I will use this application to convert the executable file generated by compiler, convert it into assembly, and then reverse this assembly into C code. So I can see what the compiler did to my code, how it optimized it, maybe remove some parts of it. So let's just drag and drop this. For now, before we start reversing all those executable files, let's just set the language for those executable and tell Ghidra that those files generated with Clang. By default it will choose GCC, but if it's not what you compiled in, so if you use GCC you will have to choose GCC, but if you compiled it into Clang you will have to use Clang before starting. Okay, so in order to start the reverse engineering we will just double click the file. This I will just use default and start analysis. Okay, after a few seconds everything is done. Now we can go to functions and see our main function. Here we go. Here is our main function. So Ghidra try to reverse every assembly instruction to C code. It will try to do its best to do this. As you can see, here's our logic. Now you can see pretty good optimization. So the compiler take a variable and multiply it by all values we written into our code, but did this in just one line. So here is our sum variable, the dvar4, multiplied with all values written in push1, push2, and push3 functions. So those functions are not existed anymore. We have only main file and we don't have any push function. So this is for optimization level 1. So this is the file cpp optimization level 1. Let's just close this and open optimization level 2 and look into main function. Again, the same exact steps. Wait until reverse engineering completed and then go to function, main, and here we go. Now you can see it's a little bit different right now. So little bit different. As you can see here, the optimization did something different in the calculation. Now calculation looks different because this is optimization level 2. So it manipulate the mathematical operation, maybe reorder them and do some different stuff to make it faster. Now let's do this with optimization level 3. Start analysis, yes. Now go to functions, main, here we go. As you can see, this is pretty close to what we saw in optimization level 2. Now let's just open the one without cout. So here in the last executable we just commented the cout this line of code, and we commented the include of IO stream, everything. Okay, so let's just open this and do the analysis. Let's see what the compiler did to our code. Function, main, and here we go, nothing. Main is basically just returning 0. So let's ask ourselves, can we just force the compiler to do all those calculations without using any cout or including the IO stream and so on? Yes, we can. Here main file has a return integer. It will basically tell the environment, which is Linux right now, what is the execution result of the application. Maybe if the application went all correctly, it should return some value, which is basically standard 0. If there's something goes wrong, it will execute and return other value. So let's just use this to make a simple comparison of test storage result, which is the sum value, and the expected value. So here is our expected value, which is f. This number, which is long value, equal test storage dot sum, and we will need to cast it to long. It should be unsigned also, unsigned long, which is basically ul. Let's return 0. Else let's return 55. Now let's just recompile this again with Clang. Let's now run the timing script to see how much time it would take. Almost the same result. So removing the cout and including of IO stream, std, all this stuff basically did not do anything. In terms of speed, it's almost the same result. So thank you and see you in the next video. Bye.